Okay, so the main focus is all the data should be in one place and should be a single source of truth. It handles structured, semi-structured, unstructured, and raw data. It supports fast ingestion and consumption. Schema on read, that is a very interesting feature for a data lake. So you have a flexibility while you are ingesting the data, you do not have to enforce any schema. So it allows you basically to apply different schema on the same data set and derive different insights over the period of time. Since we are talking about a huge volume of data, it is designed for low-cost storage. And it decouples the storage and compute so that they can be scaled individually. Lastly, it also supports for the protection and security rules, enforcing encryption, authorization, and authentication. So why are the organizations moving towards data lake? Some of the points are pretty obvious. The first one, increased speed and agility. As we do not have to think from a short-term perspective of how we are going to use our data. We do not have to think about the schema, how we are going to utilize our data. We can ingest the data at a high speed, and we can do quick POCs on such data. It is cost effective since it can be run on commodity hardware, and there are a lot of open source tools available for analytics. It has the facility of having diverse workloads run on the same platform. So we can use for data processing, we can use it for reporting, we can use it for machine learning, and so on and so forth. It also has a support for diverse analytic engines like Spark, Presto, Hive, MapReduce. So users can suit their skill sets. And it is scalable and fault tolerant by design. So you can add hardware. If I talk about storage like HDFS, Ceph, S3, you can add more storage without any downtimes. The redundancy is inbuilt, and hence it is fault tolerant. So what are the questions we need to ask before we go on for designing a data lake? What are the key questions that one should be kept in mind for a scalable and valuable data lake solution? First one is the scope of the platform, whether we are building a data lake, which would be a central data lake for the whole organization, or we are serving individual business units within the organization. The target users for the platform again plays a very important role. So whether it would be data scientists, it would be data engineers, it would be BAs, business users, etc. And how does that impact us? If suppose we are talking about business analyst as a user, as an end user, they might be more interested in a SQL-like interface, whereas a data scientist would need more sophisticated tools like Zeppelin, Jupyter Notebook, etc. Then the kind, the format, and the source of data, whether your data is structured, semi-structured, what are the data formats that are expected, whether it will be CSV, JSON, XML, what are the kind of data sources from where you would be ingesting your data, would be file-based, would it be REST APIs? These questions would help you answer selecting specific tools and technologies for your data lake solution. How is the quality of data delivered from the source system? Is the quality of data important from business perspective? Now, one should argue that, of course, the quality of data needs to be important, but there might be some solutions where you might be doing some log analytics, where you are only doing some searching, and you are not very concerned about the quality of data. Some fields here and there would still solve the purpose. So it's while on another use case, the quality of data might be of utmost important. So based on the use case or based on what purpose your data lake is ultimately going to serve would help you answer this. What are the data transformation and processing that is expected in terms of complexity? So if we are building a data lake, which would be ultimately doing some machine learning, where you would be learning some machine learning algorithm, you have to select your compute powers accordingly. What kind of integration patterns are required? Are we building it for batch? Are we building it for real time, for micro batch, streaming, etc.? Based on that, our design can be a real time streaming, a batch ingestion, or we might also go for Lambda architectures. One of the most important question would be also the personal data involvement and what are the requirements from security and legal perspective. Are there any data protection requirements? If so, in your data lake solution, we will have to think about data masking and anonymization. What are the frequency, refresh frequencies requirement? So based on the frequency, it will play a pivot role in designing the structure for your storage, how your folder structure would look like in different layers. And ultimately, where are you going to host your solution? Are you going to host your solution on-prem? Are you going to host your solution on cloud? Or would it be a hybrid solution? So these are some of the key questions that we need to ask ourselves, ask our clients, try to answer these questions, get the answers for these questions before moving on to the next phase for designing our data lake. Now, what should be the principles that needs to be followed when we are talking about a data lake? So the first and the most important one is scalability, because we are talking about huge volumes, variety, and velocity of data. So scalability plays a very important role. The storage and compute should be scaled independently. We should be able to have an auto-scaling solution inbuilt within our data lake. It should not be manually done. So there should be, we should use technologies, we should use design principles where we can enable auto-scaling. The next one is portability. So it should be easily portable to different infrastructures. We should have the freedom of choice of processing engines. The technologies should not be tightly coupled or integrated. We should be able to use different technologies and different platforms. So if you want to go from on-prem to cloud or from one cloud to other cloud, we should design our data lake in such a fashion that they are portable. Cost-effective and transparent. So from the business perspective, this design principle is very important, that our data lake should be cost-effective and should be transparent. So with cloud, you can pay as per your usage. On-prem, we can leverage Dockerization or containerization to make effective use of our infrastructure and hence save the costs. Next important point is standardized data ingestion and integration. The frameworks which we are using for ingestion and integration should be standardized, should be reusable, should be parameterized, should be easy to maintain, so that it helps, saves us a lot of efforts, and also help avoiding any technical debt. Ease of use for both users and technocrats maintaining the data lake. Because if your data lake is not easy to use, it's not viable for the end users. Ultimate goal is to make analytics easy and fast. Also, from the point of technocrats perspective, you should you should aim for automation for the infrastructure, as well as the ETL pipeline should be automated through CI/CD, so that if you want to build the same infrastructure again and again, we can do it through infrastructure as a code. And lastly, one of the most important one, data governance and security. So if there is no governance, it would not be late that our data lake would be converted into data swamps, and we would not be able to find any useful information out of it. We should have a view of what data is getting in and out, and it should be transparent with the help of central data management. Also, we should ensure the security of our data platform. There should be no breach. There should be proper authentication, authorization policies in place. There should be encryption, both at rest and in transit. So these were some of the design principles. Now let's move forward to see a data lake solution framework. So a data lake framework looks like this. So we would have some sources. So first block, which depicts the different type of sources. We can have structured sources, we can have unstructured sources, we can have streaming sources. Then moving next to the ingestion. So we have a lot of tools and technologies available. So in the ingestion block, we can have frameworks like NiFi. We can have simple programming modules written in Spark, in Python. We can have cloud solutions like Kinesis, Cloud SubPub, based on what type of source we are trying to ingest, whether it is real time or batch, and so on and so forth. Storage is the heart of data lake. How you have stored your data determines how efficiently you can use your data lake to derive meaningful insights. So we will be covering this topic in details as we go on with our use case and as we try to build our solution around that. So for storage also, there are a lot of options available. So for the object store, we have HDFS and Ceph for on-premise. We have S3, we have Azure, we have Google Cloud as a solution and object storage solution on cloud, and then we have NoSQL database solutions as well. Then ultimately, once we store our data, we have to process that data, do the transformation, analyze the data so that it can be further used by the data scientists, the machine learning algorithms, or for reporting. Not to forget, the two other pillars, which would be of utmost importance in a data lake framework, would be data orchestration, where we would be able to manage, schedule, and monitor our ETL pipelines. We can use, if we are running on Kubernetes, we can use something called as Argo Workflow. We can use Apache Airflow and a lot of other tools and techniques available in the market. And data governance, again, forms another pillar for a successful implementation of a data lake solution. Okay, so let's move forward for a sample use case. We are just taking a simple problem statement, trying to fit in our principles, design principles, and build out a solution out of it. So the problem statement is we have to create a central data lake capable of receiving and processing data from the below source systems. The source systems can be file, it can be databases, it can be REST or SOAP APIs. And then we have needs for the use case to join the data from different source system, and then which can be further used for reporting, exploration by data scientists, and building machine learning models. The framework should be easily portable to any on-prem or cloud solution. So let's move forward. So at the first step, we have some data sources. We have a small metadata and control logging. So we are using MongoDB to store the schema. This schema we would get from the different sources, the schema for the source systems, if required or if applicable. And we are doing the metadata and control management to track the movement of the data across our data lake. We can, for an enterprise solution where we are building a central data platform for the whole organization, we can use more sophisticated tools for data management, like we can use Atlas, or we can use, if we are on cloud, we can use Glue, we can use Informatica solution as well, and so on and so forth. So for this use case, we wrote some initial framework for ingestion in PySpark, and we are running it on Kubernetes. So we are ensuring portability here. PySpark can be easily, the modules written in PySpark can be easily ported from on-prem to EKS solution on AWS or GKE on Google. And okay, so the storage, we have the first layer, which is the raw layer. So we are just ingesting the data, and we are moving it one-to-one into the raw layer. So what a raw layer is, it's a single source of truth. We are doing one-to-one mapping with the source. There would be minimum or no transformation. So we have folders which can be time-based. So for if we are getting it daily, so for each of the source system, for each of the source system object, we can have a folder and then a subfolder which would have a date to it based on a daily frequency. If it is multiple times a day, we can use timestamps and so on. The data which is stored in the raw layer is retained indefinitely and is immutable. So basically, if we want to regenerate further layers, we can always do it through raw layer. So this is a single source of truth for us. There are no table structures which would be enforcing on the raw layer, and we do not generally do any deletions or modifications in the raw layer. Okay, So we get the data from the different sources to our raw layer. What next? How do we make use of this data? Are there any challenges here? Yeah. So first challenge would be updates and delete in databases. Since we are getting the data from the databases as well, there would be frequent updates and deletes, as for any transactional system, it is evident. So there would be multiple versions of the same data in the raw layer. There might be sensitive data that cannot be further exposed. What to do with that? Since we are using the web interfaces, there might be multiple calls through the REST APIs, which would result in different chunks of small files. And small files would always be a problem for further processing with compute engines like Spark. So how can we solve these issues? So for the first one, we can use the frameworks that are available like Delta Lake, QD, and Iceberg, which are very useful for CDC, change data capture. Or you can even write your custom snapshot creation logic, where in the next layer, we would be combining the data from different versions and try to have one source of truth. For the sensitive data, we would have solutions like masking and anonymization. And for the small files, we can have a compaction job run and store the data in the next layer. The next layer is our prepared layer. So we are taking the data, we are applying the logic. Wherever we have to do the CDC, we are doing that. So basically, we are cleaning the data. We are transforming the data so we can have multiple formats. So maybe one, if we are using Spark, we might want our data to be in Parquet format so that processing can be fast. If we are using Hive, we might want ORC. So the transformation would happen in this layer. There would be deduplication of data. We would be aggregating the data. We would be doing the historization, anonymization, and schema validation. Why we have highlighted anonymization and schema validation here? Because it is not necessary that this would be applied at this layer only. This can very well be shifted while ingestion during the raw layer. Before even ingesting into the raw layer, you might have requirements from the organization for anonymization. Due to the legal requirements, you might not want to host your sensitive data without anonymization even in the raw layer. So in that case, you basically can shift it to the first layer as well. And same goes for the schema validation. You might not want to have the erroneous records in your raw layer, but this rarely happens for the schema validation. For anonymization, it is always a possibility. So in the prepared layer, as we discussed, we'll be cleaning it, masking it, different optimization formats. The main thing here is the data is still one-to-one mapping of the source. So basically, we have not joined any data. We have just cleaned it. We have converted into different formats, but still each folder or subfolder corresponds to an individual data object. What next? Now we would be having a requirement for different use case hosting by joining the data from multiple sources, which is kept in prepared layer. We might also want some fast querying or exploration through SQL-like interface. We might want some catalog and search facilities on this data, which is there in the prepared layer. So what we can do, we can again write some of the PySpark programs, joining data as per the use cases. We can use Presto as a fast querying engine with SQL-like interface, and we can use Elasticsearch for catalog and searching. So that takes us to our next layer, which is the presentation layer. And here we can make use of Presto, Elasticsearch, Spark. We can process the data, we can analyze the data, and finally, as per our use case requirement, we can keep the data in the presentation layer. So the presentation layer is basically a view of data on a domain level. You can say it as a domain level data marts, which are organized by use case and optimized for specialized analysis. Some organization might have a spatial need, where they want a very fast access, they want tabular structure, they have to have some reporting requirements, and hence they might want to push a subset of their data to a data warehousing type of solution, and then they can have another optional layer of presentation layer where a subset of data might be pushed to a data warehouse solution. So it's for fast speed over structured schema, for dashboard and reporting, and if you want some fine-grained access control, that's where we might have another layer. So on a high level, this is what we have seen so far. In a layered architecture, you'd always have a raw layer, you can have some prepared layer, and then particularly the presentation layer. All the layers are not necessary. Some organizations might as well go depending on their needs with 2-layered architecture, and some might even go for 4 or 5-layered architecture, integrating the sandboxes and prototyping zones as separate layers. So as a general principle, in raw zone, we do not give any access. In prepared zone, it is limited access for some exploration perspective. And finally, in the presentation zone, the data is basically exposed for different reporting requirements. So this is how we can give the data for the different user interface. And ultimately, the data orchestration is one of the important points which we discussed in our design principle. So we at Adastra, for this particular solution, we are using a CI/CD pipeline. These are the building blocks of the CI/CD pipeline. As a first step, we are committing the code to a central repository. We have 2 different repositories, one for the application code and another for the ETL pipelines. Bamboo is basically building our code and pushing it into Docker Hub. The ETL jobs are continuously monitored by Argo CD for any changes and are pushed to Argo workflows. The Argo workflow at the particular schedule time trigger the workflow job on Kubernetes, and it submits the job to Kubernetes, where Kubernetes creates the driver pods, requests for the executor pods, and creates the executor. We have another use case which we have just for example, where we have another use case for machine learning, which was hosted on AWS platform. We have a landing bucket, then we have EMR and Lambda functions for transforming the raw data to the consumable form. And then for the metadata solutions, we are using glue crawlers, and then it can be interactively, you can do the data exploration through Amazon Athena, which can again use the glue data catalog, and there can be reports that can be pushed to QuickSight. Apart from that, a subset of the data is being pushed into Amazon Redshift for faster access, and further processing can be done to Amazon EMR, and you can use these through Amazon SageMaker and deep learning for your machine learning algorithms. So that's all from my side, and we are open to any questions you might have.
Right, thank you very much for this talk. I don't see any questions in the Q&A. If you have any, please enter them now. Maybe one quick question while we wait. So this looked like a very complex architecture. So are you helping your customers to implement and operate, or who's operating such a platform later on? Is this also you?
Yeah, we are also supporting. So we are consulting for the design, and we are also supporting for the end operations, maintenance of these data lakes, and so on and so forth. So it is not only for the designing principle, we help them to implement this infrastructure, this data lakes, and also we are helping them to maintain it. Yeah.
Okay, good. Yeah, because that's looked very complex in the end, right? So lots of moving parts in there.
That is where we are here for, making it more
Exactly,
simpler,
yeah.
and yeah.
And I saw customers in the past failing to operate this efficiently. So I think it's very good to have somebody who's doing this cost efficiently.
Yeah.
All right, I don't see any more questions, and I think we're over time anyways. Though thanks a lot for your talk, very interesting. And I hand back to Mr. Tomic, I think,